Okay, thanks. Thanks, Eric, for the invitation to speak. So I'll be talking about degree assortativity in networks of spiking neurons. This is joint work with Christian Blash, who's just finishing up as a PhD student, and Sean Means as a postdoc. So some very simple background to start with. We're interested in networks of neurons. So one important point is that these networks are directed, since connections go from one neuron to another, unlike many networks that people study which are undirected. So a neuron has an in degree, which is the number of connections coming into it, and an out degree, the number of neurons it connects to. And what we're interested in is the effects of correlations between these degrees, otherwise known as degree assortativity, on a network's dynamics. That's the general question. So assortativity, if you haven't seen it before, just look at the two pictures on the left. These are for undirected networks. So the number there refers to the degree of a single node, the number of connections coming into or out of it. And then the top left, what we see is assortative connection. So we have a low degree neuron connected to a low degree neuron and a high degree neuron connected to a high degree neuron. Whereas in the bottom left, we've got a disassortative network. So we have low degree neurons connected to high degree neurons and vice versa. But once we move into directed networks, we have four possible cases, which are in the right column there. So basically for the presynaptic and the postsynaptic neuron, you have an in degree and an out degree. So there's four possible combinations of things to look at. So if we look at the top one there, for example, we look at the red connection going from the left to the right. Given the degrees, there's already some probability of that connection existing. But now what we're going to do is say, well, let's look at the in degree of the presynaptic and the in degree of the postsynaptic neuron. And if they're both above average, for example, we might bias the probability of having that connection, make it greater than just by chance. Or if they're both lower than average, we might increase the probability of that being by chance. So that would be what we call positive assortativity between the two in degrees. And then going down, we have all the other possible combinations. So the second one down, for example, we look at the out degree of the presynaptic neuron and the in degree of the postsynaptic neuron. And again, look at whether they're both above average or below average, and then bias the probability of that connection. So what are the networks we're looking at? Well, we're looking at networks of theta neurons. There's n theta neurons. So those are the equations there in the top line. It's a normal form for the SNCC bifurcation. So each neuron is described by a single angular variable theta. We have these constant currents eta, and then the other current which comes in from the connections, that's the ij there. So it's of this form. So what we do is add up these pulsatile functions. So 1 minus cos squared, that's a function that peaks around theta equals pi. And then we have the connectivity encoded in this matrix here, the connectivity matrix. So this is just a matrix of ones and zeros. So it's 1 if neuron n connects to neuron j, and 0 otherwise. So we have a coupling strength and just a normalization here with the mean in degree. So we're going to reduce these. So skipping over a lot of the theory that I'm sure other people will talk about, Scott Hanton and that. So use the fact that these equations involve only sinusoidal functions of phases. Assume that our eta j's, these ones here, come from a Lorentzian with some mean and width. Then we're going to average over an infinite ensemble of networks with the same connectivity but random etas, and we derive these equations down the bottom. So these were already derived earlier by Barlev et al. For a different network. It's the same idea though. Basically, we get equations for the expected value of ETI theta, this quantity here at each node. So we've got the same number of equations as we had before. These are now for complex variables rather than phase variables. So the parameters of our Lorentzian come in here. The connectivity is still here, and this thing in the square brackets is really just the 1 minus cos squared, rewritten in this form here. So now we're going to lump these equations by degree. So we're going to assume that the state of a neuron depends only on its in and out degree. So what that means is all neurons with the same degree pair behave in the same way. And if that's true, we only need ND variables to describe the network, where ND is the number of distinct degree pairs. So we let Bj be the expected value of EDI theta for neurons at the jth degree pair. We need some evolution equations for these complex numbers, the Bj. So we use this sort of idea terminology from equation-free methodology. So lift from B to Z using this multiplication by a matrix capital B with its dimensions there. So basically what we're saying is if you know the n degree of a neuron, you just assign it the corresponding value of the order parameter for that degree pair. If we know Z, we can evaluate the right-hand side of our differential equation governing the dynamics of Z. And then we can restrict by averaging the dynamics of the neurons with the same degree pair. So we're doing the same thing. We're saying all neurons with the same degree have the same evolution. So it's this kind of averaging again, where we multiply the right-hand side by another matrix C. So symbolically, we have this equation at the bottom. So C times P is the identity, but they're not square matrices. You can do some algebra and show that actually that equation there can be rewritten in this form for the individual components of our vector B. And the thing is, this is the same form as our equation we saw previously for the Z's. The only difference is now we've got a different matrix in here. Instead of A, it's this matrix E, which is the product of C times A times B. So there's no assumptions on a network structure. It's all contained in this connectivity matrix A, and if I know A, I can work out E. So now I've got ND coupled ODEs. We're going to do standard bifurcation analysis, follow the fixed points, and detect bifurcations. So we want to create networks with assortativity. So we first choose our distributions, the n degree of the out degree, randomly wire up the network, remove self and multi-edges. So just practical purposes, we're going to look at networks with 5,000 neurons, the n degree and out degree both chosen from our power law distribution truncated between 750 and 2000. If you do that, you end up with very large matrix E. It's very large and very sparse. So just saying, to get around that, we lumped our degree space into 10 by 10 clusters, 10 in each of the in degree and out degree directions. So how do we get assortativity in a network? Well, we wire it up randomly, and then we go through this process of randomly choosing two edges. We'll call them I and J here on the left. So this is a way of inducing correlations between the n degrees of our neurons. So if you look on the left, we've got a high n degree neuron connecting to a high n degree out postsynaptic one, and a low n degree connecting to a high n degree. And we don't really want that, so we swap these two edges here. So connect the one with high n degree to the one with high n degree, one with low n degree to low n degree. So that's going to induce assortativity of this form. And we just do that over and over again, randomly choosing edges and swapping them if it's desirable. So as the correlation is varied, so it's a network connectivity described by A, and that's our matrix E. So we basically get a parameterized family of matrices E. So computationally, we're going to decompose E using singular value decomposition in this form here. And you find it's well approximated by a rank 3 approximation. So this large matrix E can be written as these 3 column vectors, 3 by 3 diagonal matrix, and 3 row vectors. So if we look at the singular values, for example, here are 4 different sorts of assortativity, and we're plotting the singular values as a function of the assortativity we've induced, both negative and positive. So you can see up to about plus or minus 0.5, we can just use the first 3 singular values to approximate our matrix E. So the point is we use interpolation, and we can quickly reconstruct E for any values of R we want. So here are some numerical results. So horizontally, we've got E to naught, which is the mean of our Lorentzian. So that's the overall drive to these neurons. And then vertically, we've got the mean frequency over the whole network. So this is with excitatory coupling, so positive feedback, and we get this typical bistability. So there's a region of eta naught values where the network can be either firing at a high rate, so that's the solid curve, or a low rate, that's the solid curve at the bottom, or the dashed curve, which is unstable in between, separated by these two saddle node bifurcations. So we've got our four sorts of assortativity here, and you notice the bottom two here, there's no effect of the assortativity. So the three different curves here correspond to three different values of assortativity. The top two, the assortativity does move these bifurcations around a bit. And we can see that better if we can actually use assortativity of the network as a bifurcation parameter and do continuation of these bifurcations as the properties of the network change. And we see on the left, these are the saddle node curves. So this region B is where the system is bistable, so it basically reduces the bistability region. Or in this case, it moves them around slightly. For inhibitory coupling, so that's a negative feedback, if you like. What we see is oscillations in the mean frequency. So the overall network fluctuates periodically in time. What it can do, so we've got Hopf bifurcations. So if you look at this one up here, we've got steady state here, and then Hopf bifurcation. So this is the maximum and the minimum of the average frequency over one oscillation cycle. And again, we see for these two sorts of assortativity, on the bottom, it actually has no effect on the dynamics of the network. And up here, we see a slight effect in this one and a more pronounced effect for the in assortativity. So this is a zoom showing a bit more detail in here. So this is a SNCC bifurcation of the network itself. So we see here the period going up to infinity as we approach this bifurcation. And again, we can treat our assortativity as a bifurcation parameter and continue these bifurcations. So here on the left, we've got the most complicated situation. So we've got saddle node bifurcations, black, blue are Hopfs, and then home clinic is the red curve here, and we've got various codimension 2 bifurcations. The one on the right, the curves do move a little bit, but not much. So that's our overall conclusion from these numerical explorations, that the degree of assortativity involving the out degree of the presynaptic neuron, what we call out in and out out, has no effect on the network's dynamics. The in-out assortativity, so that's correlating the in degree with the presynaptic, and the out degree of the postsynaptic does move bifurcations slightly, but the most significant effects we see are caused by creating correlation between the in degrees of both the presynaptic and the postsynaptic neurons. So just to summarize, what we did was we looked at a network of theta neurons, and we showed that they can be described by a set of ODEs describing the order parameter at each node. So that's our first equations that we had here. So like I said, this is a general technique. It's been done before by several groups, basically taking expectation over an infinite ensemble of networks with the same connectivity, the same network, but different realizations of our random etas in this case. Then we lumped by degree. This was our assumption that for large networks with large degrees, that seemed a reasonable thing to say, that the dynamics of an individual neuron are only affected by its degree. We initially thought it was only the in degree, but as we see, the out degree of a neuron can affect its dynamics if it's correlated with other things. And then we coarse-grained in degree space. So this provides a framework for the efficient investigation of the networks of the effects of network structure. In this case, degree assortativity. We've done more work on this, looking at correlations between the in degree and out degree of a single neuron, not between the in degree and out degree of two connected neurons. And we're working on other aspects of this, other generalizations of this. So theta neurons, that's the normal form of a SNCC bifurcation. So we expect similar networks of type 1 neurons to behave similarly. And if you want any more information, there's a paper that came out quite recently in this special issue of the Journal of Computational Dynamics, and the details are there. So I think that's the end.
Okay, thanks a lot, Carlo, for this exciting talk. We have plenty of time for questions. Sarthak wrote a question in the group chat. What does the structure... Oh, so Sarthak, maybe you can unmute yourself and ask this question.
Hi, yeah, so I was just asking, so at least my understanding is that it's the structure of E that is going to control the complexity of your reduced system of equations, right? So what is, I mean, and before the degree lumping, so what does E look like? I didn't really get any intuition for what the structure of the matrix E is like.
So
is it something to do with like some sort of network-based property? Then can I get some estimate for the sparsity of E?
The sparsity of E, it basically depends on how many different degree pairs you've got. So if you look at our example, say the n degrees are restricted between 750 and 2000, I think. So whatever that is, 1250 possible n degrees and 1250 possible out degrees. So if you think about the number of pairs, that's more than 1 million. And we've only got 5,000 neurons. So you're trying to fill basically a million boxes, but you've only got 5,000 neurons to do it. So it's going to be extremely sparse. So that's why we had to lump together. It's kind of meaningless, I think, to do it without lumping it together, because you just have a very large sparse matrix. It's not really representative. I mean, it certainly doesn't give you any sort of dimension reduction either. In fact, it's the opposite. So perhaps I can say a little bit about how you create the matrix E. I didn't really say that. I just said it was the product of these three matrices C, A, and B. So if we look at B, so its size is n by nd. So basically, so B, the vector B, has nd components, one for each degree pair, and then it basically assigns. It just says for each neuron, just look up the index of your degree pair and assign that value to Z. And then A is obviously the connectivity, and then C is the restricting. So the matrix B, I think it has in each row there's one entry, and that entry is 1. Whereas C, the averaging matrix, so think about that, that's normally a tall matrix. And it has, well, the rows add up to 1. And it's basically 1 over something, where something is the number of neurons with that same degree pair. So I hope that gives you some insight into what E is. It's kind of hard to visualize E or really say what it is, but it's, yeah, that's the description of how you calculate E.
Thanks.
Okay, so the next question is by Kostas Spiliotis. I'm switching to live mode. Kostas, can you hear us? No, that doesn't work. Hang on. Kostas, can you hear me? Kostas? Okay.
Yeah, now it's possible.
Yes, please phrase
Okay,
the question.
Okay, the question is, as I understand, the analysis was about the theta neurons.
Yeah.
But if we have, let's say, more complicated neurons like of Hawking-Huxley, I mean, I will try to analyze the basal ganglia network, which has a lot of complex neurons, and I have done using complex network, which have also degree in and degree out, and I'm interested for the mean field solution. I mean, to obtain a bifurcation diagram concerning the firing rate. But can I apply this approximation? I know there are different areas to model. I have done this, but always the problem of heterogeneity of network. That this is my main problem. So the question is, it is possible to apply your method?
Well, if the Hodgkin-Huxley neurons are near a SNCC bifurcation, then yes, it should go through because the theta neuron is the normal form of the SNCC bifurcation. But away from that bifurcation, then no, the neurons won't be well described by theta neurons. So the general Ott-Anderson theory won't go through. I'm not sure about this idea of lumping by degrees. I haven't really thought about what's on the current screen, applying that to other types of networks. I mean, it kind of surprised me that it worked. We went through and derived these equations, that it's basically the same equations as for the full network. So that surprised me. I'm not sure whether maybe other people can say that's obvious or it's known. So I'm not sure. I don't really know whether these ideas will work in general.
Okay.
Thank you very much.
Thank you, Carlo. Are there any more questions? Then please raise your hand. We'll just wait a moment. Okay. It does not seem that there are any further questions at this time. Please remember, you can always send an email to Carlo or any of the other speakers and phrase your question personally.
And I'd just like to acknowledge Southek, because we took basically his work and generalized it. So thanks.
Okay, I'm sure we'll hear more about that. Thank you again, Carlo, and I'll just clap for you jointly for